Okay, welcome back to Mathematics 1229. This is the third lesson on section 1.2, vector multiplication. The next type of multiplication we'll talk about is something called the cross product. So it's the third way of multiplying vectors. The first way was scalar product, the second way was dot product, and now we have this cross product. And it's by far the strangest one. One thing that makes it strange is it's only something that we can do in 3D, so only with two vectors that each have three components. Here's the formula for it. So just jump right in. Here's how it's defined. The cross product between u and v is given by this mess. The second component of u times the third component of v minus third component of u times second component of v. I'm not going to read the rest. It's all kind of like that. You can, well, maybe not this year, but in most years, if you were to walk around campus, main campus at least, you would find some students walking around wearing a hat or a shirt that has this formula on it. Those are probably engineers. It's a formula that it's not that hard to memorize, but there's another way to construct the formula that I think is a lot easier to manage. I'll show you what that is in a moment. But for the first example, we're just going to use this formula. Find the cross product of the vectors 3, 1, 0, and v is 2, 2, 1. So we're going to directly use the formula. We're not going to worry about what it means. We're not going to worry about like why are we doing this? Like, what is this cross product accomplishing? It's not the cos of theta. We already did that. Is it the sine of theta? Is it the tan of theta? Does it have anything to do with theta? Just wait. Okay, so let's see what happens. According to the formula, u cross v will be equal to, and actually I should start by indicating what all these letters are, what u1, v1, and etc. are. So 3, 1, 0, that means u1 is equal to 3, u2 is equal to 1, and u3 is equal to 0. v equals 2, 2, 1 means v1 is equal to 2, v2 is equal to 2, and v3 equals 1. So we're going to use those definitions inside our formula. I think I need more space for the formula, at least if the formula is written out that way. So u cross v is going to be u2 times v3. So u2 is 1, v3 is 1, minus u3, so 0, times v2, which is 2. So that's our first component. Now, comma, second component, we have u3, v1. So u3 is 0, and then v1 is 2, minus u1 v3, so 3 times 1, comma, I have to squish this one in, I have u1 v2, so 3 times v2 times 2 minus u2 v1, so 1 times 2. That fit, okay. Now we simplify. 1 times 1 minus 0 times 2, comma, 0 times 2 minus 3 times 1, comma, 3 times 2 minus 1 times 2, and we get our final answer, 1, negative 3, 4. Lots of things can go wrong when we do this. For example, I may have miscopied some numbers. I may have thought I put v2 and I accidentally put u2, or I accidentally put v3. I could also make a mistake multiplying. I can make a mistake adding or subtracting. Fortunately, there's a way that you can check your answer. I'm going to secretly check. I'm not going to tell you what I'm doing, but I'm going to do it on the slide. So it's kind of like right now it's just a secret, but later on it won't be a secret. You look back at this, if you review it and be like, aha, okay, I know what you're doing now. So let's see, I got 3 plus negative 3, so 3 minus 3 plus 0 is equal to 0. Okay, that's good. And then the next one, we have 2 minus 6 plus 4 equals 0. That's good. Okay, that means it's probably right. It can only be off by a minus sign. What I did is I took the dot product of this final answer, 1, 3, negative 4, with u. That was the first line in blue at the top. And then I did the dot product with v, and both of them gave me 0. It's kind of a preview of something. Okay, as promised, here's the second way to do it. The way that doesn't require you to write out all the subscripts. It's shown in general on the left-hand side. I'm not going to read through that. You can read through it on your own. I'm just going to follow that process on the right-hand side with these particular numbers, for these particular vectors. What I'm going to do first is I'm going to make 2 copies of each vector. I'm going to make a copy of the vector u side by side. So I'll try to match up what's here. I'll put a different color, 3, 1, 0, and I put a copy of the same vector beside it. 3, 1, 0. I gotta leave space between the numbers so you don't think the 3, 1 is a 31 or the 1, 0 is a 10. It's enough space you can distinguish a 2-digit number from a 1-digit number. Underneath, I'm going to put 2 copies of the vector v. So 2, 2, 1, 2, 2, 1. Now what I'm going to do is I'm going to cross out the first pair and the second pair. Then I'm going to put some brackets underneath. Put a comma, and then I'm going to plug in some numbers into there. This is going to look strange, but it's neat. So first number I'm going to get is multiplying 1 times 1, so a diagonal arrow from the top left to the bottom right. So 1 times 1. And then I'm going to, in the next position, to the right, I'm going to multiply 0 times 2. Oh, I've got to be careful with the dots again. There I go with the dots. Bad habits. So 0 times 2. And then in the last part, I'm going to put 3 times 2. Then I'm going to put a subtraction in between. So minus, minus, minus. I ran out of space. It's okay. And now we'll do the next part. I don't think I can match that color. Can I? I'll use green. Okay, so the next part, I'm going to go from the bottom left to the top right with 2 times 0. So 2 times 0, and then 1 times 3, and then 2 times 1. Okay, now we can simplify. So 1 minus 0, comma, 0 minus 3, comma, 6 minus 2. So I get 1, comma, negative 3, comma, 4. 1, comma, negative 3, comma, 4. So it's the same because it is a different way of writing that same formula. So you want to practice doing that a little bit. And it's actually a good practice for something we'll do later. This type of weird way of writing a formula. Okay. Let's do another example. This time we'll do the cross product, u times v, and we'll confirm or not confirm. We'll see what happens. We'll do an experiment. We'll see what's v cross u. We'll see if we get the same thing. We'll see if order of multiplication matters for this operation, because it didn't matter for dot products. It doesn't matter for numbers. Should it matter for cross products? Maybe looking at the definition would tell you, but we'll do an experiment. Okay, so first u cross v. 1, 2, 5, cross 2, negative 2, 3. So I'm going to do that thing where I make 2 copies. 1, 2, 5, 1, 2, 5. And then 2, negative 2, 3, 2, negative 2, 3. And we destroy the first and the last pairs on the left and the right sides respectively. And put a little bracket up here with some commas and maybe a little bit more space. But this time I'm going to do the subtractions or the multiplications rather all at once. So use the same color scheme. 2 times 3, so that's a 6. 5 times 2, that's a 10. 1 times negative 2 is a negative 2. And now we're going to subtract the next pieces. Subtract, subtract, subtract. And we have our up products. I call them up products and down products, even though the arrows aren't really necessary, but it doesn't matter. So negative 2 times 5. We have a negative 10, so we're subtracting negative 10. 3 times 1, that's a 3. And 2 times 2, that's a 4. And let's see what this simplifies to. So 6 minus negative 10 is 6 plus 10, which is 16. 10 minus 3 is 7. And negative 2 minus 4 is negative 6. I'm going to do a quick dot product in my mind this time. 16 plus 14 is 30, minus 30 is 0. Okay, and I won't bother checking u dot v. So I'm pretty happy that this passed a very easy type of test you can apply after doing a cross product to make sure you didn't miss anything or make a mistake multiplying, make a mistake adding. Make sure the dot product of what you just got with both the inputs is 0. That's the guarantee. Okay, let's do the other one. Let's do the other order now. That v cross u, 2, negative 2, 3. And you may think that we're just wasting time. That obviously it has to be the same, right? Like, how could order multiplication matter? Okay. I'm going to make 2 copies. This time 2, negative 2, 3, 2, negative 2, 3. So that one goes on top this time. And on the bottom, 1, 2, 5. Okay, and cancel. Cancel. Now we'll do the down products. Negative 2 times 5 is negative 10. 3 times 1 is 3. 2 times 2 is 4. And now the up products. Well, I got the minuses in there, so subtract, subtract, subtract. We subtract the up products. 2 times 3, 6. 5 times 2, 10. 1 times negative 2, negative 2. And then we simplify. So negative 16, negative 7, positive 6. It's not the same, but they're related to each other. What's the relationship? One is the negative of the other one. This process we just went through doesn't prove that this is always going to happen. Now, it does always happen. It's always going to be the case that u cross v is equal to v cross u. In order to prove it, it's not that hard. Instead of putting numbers in, 1, 2, 5, 2, negative 2, 3, you'd leave it with letters. So A, B, C, D, E, F. Do the cross products and compare them, and you would see that the order will result in one being the negative of the other one for any values of A, B, C, D, E, F. So that's how you would prove it in general. Or at least one way to prove it. There's other ways. So I'm going to write down what our results were. U cross V, we got 16, comma 7, comma negative 6. And v cross u, we got negative 16, negative 7, positive 6. And this is, again, not an accident. It's not a fluke. It's not something that just happened this one time and it's not going to happen again. It's always going to happen that u cross v is equal to the negative of v cross u. So any vectors in R3 will have this nice property. Okay, it turns out that this vector that's created from these two input vectors, so the new vector that comes out of this operation, will always be 90 degrees or orthogonal to both of the input vectors, both of the things that we combine to make this new vector through the cross product. We test this nice property of cross products by using the dot product. We take this resulting vector that we get from doing the cross product and then dot it with the input vector u and separately dot it with the input vector v. If we did our calculation correctly, then both of those dot products will result in 0. This will always happen, which tells us, and you can again go back to the A, B, C, D, E, F thing and prove it in general, this tells us that the cross product of two vectors always creates a new third vector that is simultaneously orthogonal, simultaneously 90 degrees to the two input vectors. Oh, yeah, I changed the vectors somewhere. For the vectors below, so for the vectors below, that u cross v is orthogonal to both u and v. So they're telling us what u is, they're telling us what v is, and they're telling us what u cross v is. You can confirm this if you want. Homework. Confirm this cross product. But we're just going to take it. We're going to take it as a gift. Thank you. Thank you for the cross product. Now we're going to confirm that this new vector is orthogonal to both u and v. So we're first going to check if u cross v is orthogonal, if it's 90 degrees, to the vector u. So we're going to have negative 3, comma 6, comma negative 3 dot the vector u, 1, 2, 3, equals 0. Let's make sure. So we got negative 3 plus 12 minus 9 equals 0. Yep. Negative 3 minus 9 is negative 12. Negative 12 plus 12 is 0. 0 is equal to 0. So it's true. All that we've done so far is we've shown that u cross v is orthogonal to u. We're not done yet. We also have to check if it's orthogonal to v. For this, we need that u cross v dot v is equal to 0. So let's check that. Negative 3, comma 6, comma negative 3 dot 4, 5, 6 equals 0. We're going to make sure this is true. So we have negative 12 plus 30 minus 18 is equal to 0. Negative 12 plus negative 18 gives us negative 30. Negative 30 plus 30 is 0, so 0 is equal to 0. True. So we're done. We proved that this output vector, u cross v, is orthogonal to u and orthogonal to v. Okay, and we'll do one more example and then cut to the next video. Remember those I, j, and k vectors? Well, in this example, you're asked for a cross product between I and j. Without the cross product operation, the question would be ambiguous. I could represent a unit vector in the x direction in 2D or 3D. J can represent a unit vector in the y direction in 2D or 3D. When we add the cross product in there, if this operation is to be defined, then I and j both must be in 3D. So we have to have 1, 0, 0 cross 0, 1, 0. We can infer that from the context of the question. Okay, and I'm going to leave some spaces, do the usual thing. 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. Destroy the first and the last. And then we have our down product, 0. Our next down product, 0. Our next down product, 1. And we have our up products, 1 times 0, 0, 0 times 1, 0, and 0 times 0, 0. And we're supposed to subtract all those second pieces. Subtract, 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 and we can simplify 0, 0, 1. And what's that? What do we call that? We call that k. And that's a nice result because we can geometrically picture this. So here's your picture. We have the vector I going left and right. We have the vector j going up and down. Maybe we can't picture it. It's hard to picture in 3D, but I'll do my best. And then coming towards us out of the page. I don't know, when I was in elementary school, I used to draw these like 3D boxes. Used to do this and like connect the lines. And sometimes we'd do this. We'd be like, yeah, let's put the little dots in. I don't know. Maybe people stopped doing that. But, so picture that. Picture those types of images. We're going to draw this little diagonal piece out coming towards us, coming out of the page. Imagining it has some depth to it. That's k. And the angle between I and j is 90 degrees. The angle between j and k is 90 degrees, and the angle between I and k is 90 degrees. They're all 90 degrees to each other. So we put an I vector and a j vector across them and got an output that is simultaneously orthogonal, or simultaneously 90 degrees to both of the inputs. Anyway, we'll stop here and continue with the next video.